So now I've turned on the recording. Okay, so now we can start today's lecture. Okay, I will minimize this as well. So last time we briefly talked about the concept of informed search or the concept of heuristics. Okay, so one major concept about heuristics is that it is the know-how obtained through a lot of experience, and it actually allows us to act quickly without thinking deeply about the reason or without thinking at all. Okay, sounds very lot of technical jargons, but you just understand this. Okay, heuristic is something like this. Okay. So when you are playing card games like poker, okay? If you are experienced in poker enough, okay, you can actually sense what card that your opponent is having. And you can do it with an instant without doing explicit mathematical calculation in your mind. Okay? You can observe your opponents and you can somehow have a sense of what your opponent is having without doing a lot of complicated mathematical calculation in your head. Okay, so those things are called heuristics. Okay, something that allow us to get a approximate outcome of the game without really doing a very expensive, computational expensive operation in our mind. Okay. So for example, when you are playing poker, you would not do a complete recall on your memory on what cards your opponent have taken and what cards you have taken in order to guess what kind of cards that your opponent is having. If you are experienced enough, you can kind of guess, have an educated guess on what your opponent card is having without a complete back tracing of what the game really happened before. Okay, so this kind of educated guess will be called heuristics. Okay, so that is the reason why we'll also say that heuristics are so-called tactical knowledge that cannot be explained verbally. Okay, okay. So for local students, okay, when you are playing mahjong, okay, you actually would need to kind of sense what your opponent is having, okay, is having, okay. For example, in a game of mahjong, okay, okay, you will need to win the if you will need to will essentially need to have a combination of the cards such that you can win the game. Okay, and there are two ways to win the game. Okay, the player can obtain that card from taking the card from the deck. Okay, that is the first way you can win in a mahjong game. Or you can wait for your opponent to discard a card that you want, okay? And if a player discarding a card that you want, okay, in order to win the game, and you realize that, and you grab it, okay, then you win the game, okay? And the player who discard that card will lose the game, and he will lose a lot of money, okay? So in order not to lose money in mahjong, you kind of need to have a mindset on what cards your opponent is trying to have, okay, and try to avoid discarding the card that your opponent wants, such that you can avoid losing money. In Chinese, that will be 你要睇下究竟你嘅對手要咩牌就冇出衝咯。OK。So because the term is really difficult to explain in English, so I use I have limited use of Chinese right here, okay? But this is just a illustrative purposes of heuristics, okay? So when you are playing mahjong, when you are guessing what cards your opponent want to have, you would not do a complete look up, complete review on what exactly has happened throughout the mahjong game. You kind of able to guess what your opponent is expecting to have based on your intuition, based on your instinct, based on your experience. Okay? Okay? And so those are actually called heuristics. Okay? Okay? And essentially, when we are working with computers, we want the AI to have this ability as well. We want the AI to able to have to do educated guess when it is doing search to optimize its performance. Okay? The core idea is that if the AI is able to make educated guess on doing a action is better than other action, then the AI can possibly avoid doing some unnecessary actions and doing some unnecessary search and get to the result faster. Okay? And that is exactly the thing we want to replicate in the AI. Okay, in humans, we can use the heuristics to avoid doing unfavorable actions. Okay, for example, when you're playing mahjong, you can use your heuristics, use your experience to guess what cards that your opponent wants and avoid discarding those cards to avoid losing money. And you do all this by a hunt of guess, okay, by guessing, by educated guess. And we also want to incorporate this ability to AI. We want the AI to have the ability to do an educated guess on the action, on what kind of outcome that the action will bring to the AI. Okay, we want this. We want the AI to able to do some educated guess such that it knows what way is bad and what way is good, and it avoid doing the bad things and keep on doing the good things such that the efficiency can be improved. So that is what we want about the heuristics. Okay. At the end of the day, when humans playing games like mahjong, we would kind of guess what cards that our opponent is having and what cards our opponent want to have. And we want to avoid giving those cards to our opponent such that we avoid losing money. In Chinese, it's 打麻雀嘅時候，我哋唔想出衝 ，OK？ So we'll use our experience to guess what card that our opponent wants to avoid losing money. And that is done without the complete calculations of what has happened throughout the mahjong game. You kind of able to do educated guess with your experience. Right?
So is it the same as in the psychology? It's just a mental shortcut.
Yeah. So we want to replicate this mental shortcut in our AI. Okay? And the reason is that we can make our AI avoid making bad move. Okay? Avoid making bad move. If we can have such a mechanism built into our AI, then our AI can completely avoid or reduce the priority of bad move such that it can concentrate on the good move and it can get to the solution faster. So that is what we really want. And we will replicate this behavior by using approximation. So we know that finding the exact results of a problem is difficult. but we can kind of create a function to estimate the outcome of the problem or the outcome of the action without the exact result. Okay? If we are able to kind of estimate the final outcome of the of the whole problem of the actions with a very low computational cost, then we can use this approximation to lead to reduce the priority of bad move such that our AI can always choose the good move. So this is the whole idea here, okay? This is the whole idea here. We use approximation, low computational cost approximation to kind of calculate the outcome of an action. Then we do a sorting on the actions. If the action is already estimated to be a bad move, then we reduce its priority. Okay, simple as that. So this is the whole idea. Okay. And in fact, this approach have been used in many situations. For example, when the Google is creating the AlphaGo to play the game Go, okay? Okay, that is okay. Actually, in the field of computer science and data science, the game of Go is an extremely difficult problem to solve. Okay, when I was studying in my undergraduate, for my undergraduate, okay, my professors actually taught me that in the near future, no one will be able to write a program to be able to conquer the game of Go because the game of Go is so complicated to do. But of course, Google is somehow able to figure out a way to do so, okay? But let's just say that the game of Go is a very difficult problem, okay? And if you are relying on traditional search algorithms, really going through all the possible pathways and selecting the right pathways to win the game, then that will be extremely tedious. Okay? When you want to write a program to play a game like Go, okay, or play a game like chess, okay, the approach we'll use is some sort like what has been shown in a movie, okay? So I believe that you should at least kind of know what is Avengers, right?
Oh.
In Avengers 3, okay, the Avengers 3 movie, okay, the main characters, the Avengers, are being defeated, right? So what Doctor Strange has done? Doctor Strange had used his power to look over all the alternative universe and found one way they can win, right?
So simple.
Yeah. So this is exactly how AI play chess.
So simple.
I just compute all the possible game scenario and then list all these paths in the memory, and then I choose the one that is the best. So exactly how the Doctor Strange in the Avengers 3 beat the Chronos is the exact technique you write the AI to play the chess of game. Okay? Okay? And the issue about Go is that the chessboard is too large and the possible combination is too much that doing this approach is difficult to do. Using this approach is difficult to do. Too many combinations, okay? Infinite combinations, okay? Infinite combinations, okay? So what the Google has done is very simple. It actually used heuristics to quickly scan over the path that will not be a good move. Okay, it quickly use a heuristic to scan some move that it knows that it is not a good move, and then it remove it. It doesn't consider it. Okay, it just skip a lot of moves that it knows that is not a good move.
Is it called choice by nature?
Yeah. So So just like doing MC, you know that some answer is wrong, then you just would remove that. Okay, and such that you can speed up the process. Okay, and essentially this is what the Google have done to conquer the AlphaGo, to conquer the Go chat and able to write the AlphaGo AI program. Okay, so in fact, heuristics is something that really is being used in the state of the art AI design. Okay, okay, and if we don't have heuristics, first of all, AlphaGo would never be able to accomplish. Okay, okay, algorithms like AlphaGo will not be able to be accomplished. Okay, because this scale of the scanning, the scale of the search is way too large that you cannot handle it. Okay, and and what I would like to talk about one thing is that I understand that in your studies, okay, over your studies on programming, on AI, on algorithms, you actually have a concept in your mind that, okay, I write a algorithm, my algorithm should be able to get me an exact result. Okay, you have the mindset that when I am creating an algorithm, my algorithm should always give me the exact solution of a problem. But in fact, it depends. In some situations, we want an approximation only. Okay? For example, in the situation of heuristics, we only want an approximation of the outcome, and the approximation is used to do some preliminary filtering, do some preliminary elimination on the pathways, on the action that is not good. Okay, so in fact, you will find that many algorithms in computer science and data science are actually just approximation algorithm. They just give you approximated outcome. Okay, and you may originally think that approximation algorithms, they are just giving approximation. So how they can be used? And heuristic is one usage of those approximation algorithms. Okay, okay, okay. So one technique in data science is that if something is difficult to do, and if I want to select the best item over a bunch of items, okay, and doing the exact calculation of evaluating what item is the best is very difficult to do so, then one approach is that I use an algorithm to approximate what item is good and what item is bad. And I use this approximation to filter out the bad items. Then after I pinpointly select a bunch of candidate good items, then I run the expensive algorithm to check them out one by one. Then I can significantly reduce the amount of time that I need to select the item that I want. Okay, and this approach, it doesn't just apply in the heuristic on search algorithm. It actually also apply in the machine learning field as well. Okay, so any questions? So any questions? So if you are pursuing a PhD or MPhil in the future, you would actually will actually need to study a lot more algorithm that is heuristic or approximation nature. Okay, and that is the reason why. And just take a look on the basic general tree search algorithm. We already talked about this already. Okay, we are already go through this in the past already. And the major important factors of the general tree search algorithm is the fringe. Essentially, we use the fringe to prioritize the look for selection. Okay, so now we want to incorporate the heuristics in our search algorithm. So what we will do is that we will actually work on the fringe, okay? We just modify the fringe such that the fringe can select the nodes for expansion based on some heuristics that is done. Okay, when we are working on the general tree search algorithm, we will the most important element that will control our search strategy is the fringe. So we essentially use the fringe to control what node to select for expansion first. And we also now learn a concept called heuristics. The heuristics can be used to evaluate what is the consequences of an action. So we can merge them together. We can integrate them together. We can use the heuristics to calculate, to approximate which node is a better move. Okay? And then we select that move, and then we select that node for expansion. Okay? Then that will be the technique, that will be how we incorporate heuristics into the general tree search algorithm. We actually just modify the fringe. Okay? And the algorithm, the first algorithm that is based on heuristic that I will talk about is the best first search. Okay? Essentially, when we are working with uniform call search, we will do things like this, right? So let's get back to the uniform call search. No, not this one. This is the old one. Okay. So when you are doing the uniform call search, you are actually using, when you're doing the uniform call search, you are actually using the path, the path cost of the node. Okay, up to now so far for expansion. So for example, here in the uniform call search for the p-test, the path cost of the p-test is the cost that go from Cebu to Mitchell Creek to p-test. Okay, we actually go over this already. Wait. This one. We actually go through this already, okay? So for example, here is the search tree, okay? So if we are talking about Fagris, this node is actually representing a path from Iraq to Cebu to Fagris. Okay? Okay. In the search tree, okay, so you can see that each terminal node in the search tree is actually representing a path starting from the root node. Okay, so for example, for Fagris, this node I highlighted here, it represents a route from Iraq to Cebu to Fagris. And for the Odeus node I stated here, it is representing a route from Iraq to Cebu to Odeus. Okay, so every terminal here is actually representing a path that we have explored so far in our search algorithms. Okay, and in the uniform call search, we are using the path cost of the node that we have generated so far for expansion. Okay, and the best first search is using another technique. So essentially, the idea of the best first search is that we can use the heuristics to estimate what is the cost that each terminal node need to take to get to the goal set. Okay. So essentially, for the best first search, we actually use the cost of the node that it needs to take to travel to the goal state. When we take this estimated cost to select the node for expansion. Okay. So the idea here is that in the uniform cost search, okay, we actually consider the path cost of each path that have been stored in our search tree, and then we take the shortest path right now for expansion. Okay, okay. We take all the path that we have in the search tree right now, and we take the path that is shortest for expansion. So this is what uniform cost search is doing. But for the best first search, we do it the other way around. We actually take all the terminal node and then we check out, we compare the distance between each terminal node to the goal state. Okay? And then we select the terminal node that have the lowest estimated cost to the goal state for expansion. Okay? So we expand the path that seems to be closest to the goal state right now for expansion. Okay, we don't care about the path cost right now. Okay, when we setting the path for expansion, we don't care about the path cost of the path right now. Okay, we select the path or we set the node for expansion just solely based on whether the node is closest to the goal state. Okay, okay, okay. So we completely let the heuristics. We completely let the estimated cost to dominate our node search process. Okay. So I will go into the examples here, okay? So as you can see here, we have a in this PPT, okay, it is showing the whole execution flow of the best first search, okay? In the left, okay, we have the search tree, and on the right hand side, we have the state space. And we have one thing extra, okay? This one thing extra is the straight line distance to Bucharest. Okay? Is the straight line distance to Bucharest. Okay? So the underlying concept is that if two locations is close to each other, then their straight line distance should be smaller. Okay? Okay. And by integration, we know that if two places is close to each other, according to the straight line distance on the map, okay, then most likely moving from one place to another will not be so too difficult, right? Okay, okay, okay. But of course, this heuristic is not always correct. So maybe okay. So this is a map of Hong Kong, okay? So by our natural thing, but based on our natural thinking, okay? So based on our natural thinking, okay? If two places is close to each other according to straight line distance, then it is more likely that traveling through these two places is faster. Okay, so for example, if you are in Prince Edward right here, okay, going to Mong Kok will be far closer to going to Yau Ma Tei, okay, because the straight line distance between Prince Edward to Mong Kok is smaller than the distance of Prince Edward to the Yau Ma Tei. Okay, okay. So we can see here in the we can see here that if we want to go from Prince Edward to Mong Kok, okay, then the time distance is smaller than you go from Prince Edward to Yau Ma Tei, okay? And this is natural, okay? But this heuristic is not always correct, okay? So for example, if you want to go from Prince Edward to Jordan, okay, it will be faster than you go from Jordan to Central, okay? Okay, although the straight line distance between Jordan and Central is similar to the distance of going from Prince Edward to Yau Ma Tei. Okay, but when you go from Jordan to Central, okay, you need to cross the Victoria Harbour. So that will actually use more time. Okay, but so you can see that heuristic is not something that is always correct. But taking a calculating a straight line distance between two locations in the map is always easier than going through the actual road map to calculate the actual time needed to travel between two places. Okay? Okay. So if we actually need to calculate the time needed to go from Jordan to Central, then we'll need to consider the time needed for the MTR. Okay, if we are just considering taking the MTR, okay, then you need to consider the time needed for the MTR to go through the tunnel, okay, the overseas tunnel, okay, the tunnel over the Victoria Harbour, okay, and that calculation will be very tedious. Okay, but if we are using the straight line distance to approximate the time needed to travel from one place to another in a map, okay, it will give us a reasonable good enough estimation. Okay, but of course this estimation will not always be correct, because in some situations, if you need to go across the Victoria Harbour, then something like that, then the time approximation will not be good. Okay, but it should be reasonably good enough approximation. If you are talking about the typical normal situation, for example, here, if we use the straight line distance to approximate the time, travel from Prince Edward, okay, to Mong Kok, okay, and compare the time needed to go from Prince Edward to Jordan, okay. So naturally, you go from Prince Edward to Mong Kok will be faster than going from Prince Edward to Jordan, and the straight line distance also concur with that trend as well. Okay, so using straight line distance is a good approximation, but it just in some situation, for example, if we are considering going through the Victoria Harbour situation like this, the straight line distance will not be a good approximation. But that is a rare case, okay? And the straight line distance will be a good enough approximation in our situations. Okay? Okay? So here what I'm just saying is that if we are talking about the approximation of the distance of the time needed to travel from one place to another, you can use the straight line distance of the map of that two places to do the approximation. Okay, and I'm using the map of Hong Kong to demonstrate that in most situations, the approach will be correct. But in some situations, those approach will not be correct. For example, if you have rough terrain, like going through the sea, then going through the harbor, then those situations will not be good. Okay, those situations, the approximation will not be good. But here, using straight line approach, straight line distance to approximate the distance of two places will be a good enough approximation, and it's easy enough to compute. Okay. If I need to calculate the distance between two locations in a real fraction, in a real manner, then I would need to consider how much time I would need to take to go across the harbor, for example. Okay, and it would be far more tedious to calculate when compared to a straight line distance. So that is why circular distance is a heuristic. It does not give you a exact solution, but it is fast enough to calculate, but the approximation is good enough. Okay? Okay, so this is the kind of heuristics we are talking about when we are doing the search. Okay, we come up with something to approximate our outcome. That is the distance, the time needed to go from one place to another, with a very minimalistic computational cost function. Here we use a straight line distance to approximate that. This approximation will be good in most situations, but in some specific situations it will be bad. But we kind of accept this flaw, okay? Because the time we can save on the approximation outweigh the error that is brought upon by the approximation. Okay? Okay? So any questions? And here we are working with the Romini Turing problem. We want to find the shortest path from one place to another. So we use the straight line distance between the cities to the Bucharest to the Gold State as our heuristics. Okay, and I already used the map of Hong Kong to demonstrate why this heuristic makes sense. Okay, and now we are using the same technique, the same coding base as the uniform call search, but right now we are using the heuristic value as the priority. Okay, in the uniform call search, we do not use, we actually use the path cost of the node as the priority. But now we are using straight line distance of the nodes to the Bucharest as the priority. Okay, so this is the major change we do to the code base of the uniform call search such that it can be reprogrammed to be the best first search. Okay. Okay. And now we start with Bucharest. We start with Cebu. The approximate distance of Cebu is 253. Okay, so we put it right here, and then after we explore Cebu, we have Figueres and we have Mitrovica. So referring to the straight line distance to Bucharest table that is the heuristic function we have here. The straight line distance of the Figueres is 148 according to this table. So we add Figueres to the priority queue with 178 priority. Okay, and the Mitrovica is having a straight line distance to Bucharest of 193 according to the table. So we use the 193 as the priority value to be added to the priority queue. Okay, and because the Figueres is having a lower priority value, so that is closer to the Bucharest, so it get extracted first. Okay, remember all the distance we are talking about here are the approximated distance, because you cannot travel in the Romania between two cities really through the straight line. Okay, for example, here in Cebu, you cannot go to Bucharest directly with a straight line. Okay, okay. Unless you are living in a world that you have portal, transporters, or Doraemon's door. Okay, okay. You cannot travel through the straight distance. Okay, maybe in the future, if we have transporters or if we have portal, then you can travel between two locations in a straight line distance. But now we are working with the road map. Okay, straight line distance is not something we can do. Okay, so that is the reason why we will say that the straight line distance is an approximation. Okay, and the Figueres is having a small distance to Bucharest according to the straight line distance, but not with the actual path cost. So we expand that first. Okay, and we found that the Figueres is having one way to the Bucharest having one route to the Bucharest only. And of course, the straight line distance between Bucharest to Bucharest is 0. So you can see that we add Bucharest as 0 here. And because the Bucharest is having 0 cost, so next time we will expand Bucharest first. And because Bucharest is our endpoint, so we end the search. Okay. So you can see that the major differences between the best first search and the uniform call search is only one line. It's only the last line. In the uniform call search, we would actually use the path cost or the node as the priority value. But here we are using the heuristic function value as the priority. Okay, so in the best first search, we just believe the approximation is good enough to select the good path for expansion. Okay, so this is the major difference. In the uniform call search, we rely on the information we collected so far during the search. Okay. So we don't have extra information other than the information we generated throughout the search. Okay, remember the uniform the path cost of the uniform call search is calculated when we are building the search tree. Okay, so all this information you use for prioritization in the uniform call search are actually generated along the search. So no extra information is being taken to help you with the search. You are using all the information you generated during the search to guide your search. Okay. But when we are talking about the informed search, the best first search, when we're talking about the best first search, you are using the heuristics. Okay, we are using external information to guide your search. Okay. So this is the major difference between the uniform call search and the best first search. Okay, the best first search is relying completely on the heuristics to prioritize which node is good for expansion. Essentially, it uses the heuristics to select the path that is good for expansion. For uniform call search, it uses the existing information and select the route that is shortest right now in our search for expansion, for further exploration. And this is the major difference. So if you take a look on the coding of these two algorithms, you will find that they are 99% similar to each other. The major difference we have is just one argument. The best first search is using heuristics value as the argument, and the uniform call search is using the path cost as the argument. So this is the major differences of these two algorithms. Just one argument of the function has been changed. Then we convert the uniform call search into best first search. Any questions? Any questions? Any questions? Okay. So at the end of the day, writing program is not just about writing bunch of instructions. Okay. So up to now, all the algorithms you learn are essentially the same, but we are just tweaking. We are just doing minor tinkering on the fringe, and we come up with so many already four algorithms already. Okay, all these algorithms are substantially the same, but only the search strategy or the fringe for selecting the node for expansion is different. Okay, so any questions? So any questions? So any questions? But it seems the best first search is very good. Okay? But best first search is actually having its issue as well. So after the best first search, okay, you can actually do some back trace and you can actually compute the real path cost. Okay, so you can always back trace. Okay, and during the back tracing, you can always calculate the real path cost. Okay. So when we are talking about best first search, okay, the first issue about completeness is no, the best first search is not complete, meaning that it is not guaranteed to give you a solution if there is a solution in the first place. Okay, the issue why is very simple. If your heuristic is written wrongly, then you may get stuck. Okay, your best first search completely rely on the heuristics to select the node for expansion. Okay, so at the end of the day, it depends on whether your heuristic is a good heuristic or not. If your heuristic is good, then you can always get to the solution. If your heuristic is bad, then you may not get to the solution. Okay? Okay? Just like when you are playing mahjong, okay? If you are experienced player, then you can avoid discarding the cards that other opponent want and losing the game. Okay, you can always avoid that. Okay, if you're experienced player in mahjong, you can avoid making mistakes and avoid discarding card to your opponent to help him or her win the game. Okay, but if you are not a experienced mahjong player, then you may lose a lot of money because you are not able to guess correctly what your opponent is want to get from you to win the game. Okay. So if you rely the best first search completely on the heuristics, then of course the heuristics would strongly affect whether your algorithm can perform well. And as a result, we cannot say that the best first search is guaranteed to be competent. Given the fact that your problem has a solution, your algorithm may not be able to find it if your heuristic is bad. Okay? So that is why we'll say the best first search is actually not complete. Okay? And the time and the space complexity is b powered by m. Okay, similar to the best first search. Okay, and of course it's not optimal because your search again is completely relying on heuristics. Okay, so if your heuristic is bad, then your solution will not be optimal as well. Okay, the heuristics can just avoid you to go into some bad move. Okay, but if your heuristic is bad in the first place, it may recognize the good move as the bad move, and as a result, you will miss some good move at the end. Okay, so that is why we'll say that the best first search is not optimal. Okay, all your search is relying on a pure approximation, and approximation can go wrong. So your algorithm is not guaranteed to be complete and optimal, and that's the reason why. Simple as that. Okay. You rely on approximation to do things, then of course your final outcome may not be always be correct. Okay. Just like maybe I will just use a not so appropriate example. So it's like in a movie. In some movie, you will find that some students, they do not study hard enough. So what they will do is they will mark A, B, C, D on the pencil, and they will roll the pencil and to get the solution of the multiple choice question, okay? Just by pure luck, okay? Then occasionally you can get some answers right, and you can get some answers wrong. Okay, so that is similar to what will happen if you guide your search rules completely using heuristics only. Okay, using heuristics only, because you are rely on something reliable, so your solution will not be reliable as well. Okay, okay, and okay, if your heuristics is omnipresent, okay, mean that if your heuristics is always correct, okay, just like miracle, okay, then of course you can use this heuristics to get to the solution. Okay, okay. Hypothetically speaking, if your heuristics is optimal, if omnipresent, meaning that it is miracle worker, okay, it is miracle maker, okay. Your heuristic function is miracle maker. It can just predict give you a reliable solution always with the lowest computational cost. Then you can totally rely on the heuristics to do the search. Okay, but this is the real world. We don't have omnipresent heuristic function. We don't have heuristic function that can always give you a correct solution with lower cost. Okay, it just doesn't happen. Okay, so in that sense, our search with the heuristic function will lead us to do some wrong things in the search. Okay, so that is why best first search is not reliable and is not complete and is not optimal. Okay, okay. So any questions? So any questions? So any questions? Any questions? Any questions? Any questions? And essentially, we want to address this issue by a new algorithm. And this new algorithm is called the A-star search. Okay? Remember, we talked about something. In the search tree, each terminal node is representing a path, right? Okay. So for each terminal node, we already have a path starting from the initial state to each terminal node. For example, the Pythagoras here is actually representing a route from Arec to Cebu to Pythagoras. Okay. And the Odeus node is representing a route from Arec to Cebu to Odeus. Okay? Okay? And we also have the heuristics, right? We can use the heuristics to guess the distance, the path cost needed to go from any node to the goal state. Okay? Okay? So why don't we add these two measurements together? Okay? So this is what A-star search is trying to do. Okay? Within the search tree, for each terminal node, okay, you have the path cost, and the path cost is essentially the cost taken for the agent to go from the initial state to the terminal node. Okay, we have already discussed this over and over already. Each terminal node is representing a path, right? Right. So we also can have a heuristics. Okay. We also have a heuristics to estimate the cost needed to go from any node to the goal. Okay, so essentially by adding the estimated cost of the terminal node to the goal state and adding the cumulative path cost from the initial state to the terminal node, we can formulate a overall estimated cost starting from initial state to the goal state through the path represented by the terminal node. Okay. Okay. So here in this terminal node, we can use the heuristics to get the estimated cost of this terminal node to the goal state. Okay, and this terminal node itself is representing a path from the initial state to the goal to this terminal node. Okay, so if we add the path cost of the path cost or taken for the agent to go from the initial state to the terminal node and the estimated cost of the terminal node to the goal state, we actually is able to compute the overall estimated cost of the path that is represented by this terminal node right now to get to the goal state. Okay. Okay. So now we are not selecting the shortest pathways for expansion. We are estimating the total path cost of each path getting to the goal state, and we use this overall estimation to select the route. Okay. Okay. So we are having the best of both worlds. Okay, we use the heuristics we use in the best first search combined with the path cost of each path to calculate the overall estimated path cost for the initial state to get to the goal state through the terminal we are working on. Okay, so this overall estimated cost give us a better overview on each path, and we are able to select a path that can get to the goal state faster. Okay. Okay. So any questions? Any questions? Any questions? Any questions? So it makes sense, right? Okay. So essentially, for the A-star search, we combine the best of both worlds. We take the best first search, and then the uniform cost search. We take the priority value and add them up together, and that new priority value becomes the A-star search. Simple as that. Okay. 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 And here is the formula for calculating overall estimated path cost. Okay, you essentially take the sum of the step cost from the initial state to the end, and then you take the estimated or the path cost from end to the goal state. Okay, and you add them together, then that value will become the total estimated path cost of a node. Okay, and of the node n. Okay, and this overall estimated path cost will be used as the priority for prioritizing the node for expansion. Okay. So in the past, when we are working with uniform cost search, we are selecting a path that is shortest, and then we expand it. Okay. We do not consider whether this shortest path will really get to the goal state the fastest. Okay. Okay, so that is what we are working on when we are using the uniform cost search. Okay, but after we introduce heuristics, we are able to making an educated guess on the time needed for the terminal all terminal to get to the goal state. So we can use this information combined with the path cost from the initial state to every terminal node, and we are able to calculate the overall time needed. And although it's only estimation, okay, an estimated value on the overall path cost of the path needed, or all the path that we have right now to get to the goal state. Okay, and we see that the path that have the lowest estimated value, and we explain it. Okay, simple as that. Okay, so any questions? So in the whole scenario here, we are just adding these two vital information together. So now we don't just consider the estimated cost, we also consider the actual accumulated path cost, okay? So that is why the A-star search is actually optimal and complete. Okay, the A-star search is actually optimal and complete. Okay, but you need to remember one thing. For A-star search to be complete and to be optimal, it has one restriction. The heuristic function should be admissible. Okay, so what is admissible heuristics? So admissible heuristics means that the heuristics is actually smaller than the actual value. Okay, we do not overestimate things, and that is called admissible heuristics. Okay, we do not overestimate things, then that heuristic function is called the admissible heuristics. So let's take a look on this PowerPoint notes, okay? So now let's talk about the straight line distance that we have been talking about. When we are using the straight line distance to approximate the location, the cost of two items, okay? The cost need to travel between two places, okay? The straight line distance is always giving you a lower estimated value than the actual value. Okay? Because of the triangular inequality. Okay? So as you can see here, in this example, we have Cebu to Bucharest, okay? And the straight line distance between Cebu and Bucharest is 253. Okay? And if we consider the real distance between Cebu and Bucharest is 278, okay? And from this example, we can see that the straight line approximation is smaller than the actual value. And the reason is simple. In mathematics, we know that there is a concept called triangular inequality.
But it's in the metric space.
Okay, so in the map space, okay? So no matter what route you have in the real world, is always larger than the actual straight line distance, no matter what. Okay, no matter what, in the real world, you can never travel from one place to another as good as the straight line distance. The straight line distance is always the shorter distance. Okay, so that is why we'll say the straight line distance here is actually the admissible heuristics, because it is always a smaller estimated value than the actual value. Okay, and this is vital for the A-star search. A-star search will only work if you have an admissible heuristics. Okay, so you cannot have a heuristic that is bigger than the actual cost. Okay, if you want to use the A-star search, your approximate value should be smaller value than the actual value. You will never overestimate things. Okay? 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 The reason why we don't want to overestimate things is that if we overestimated things, okay, then we may overestimate the estimated cost of going to the goal state too large, that we will reduce the priority of the shortest path and select another path instead. Okay? Okay? Let's consider this. A route going to a real shortest path going to the path cost. A route which is the shortest path going to the goal state. Okay, you overestimate its path cost to be infinity. Then you will never select that route, and you will miss out that route forever. Okay, so that is the reason why you don't want to overestimate stuff when you are working with A-star search. When you overestimate the stuff, then your shortest path will get a lower priority, and you may select another route going to the goal state at the end. Because our search algorithm will stop right at the moment we get to the goal state. And if our estimated value is doing an overestimation, then the real shortest path going to the goal state may get a lower priority, and we will miss it forever if we somehow have another route going to the goal state. Okay? So imagine this. If we overestimate the path cost of the shortest path to the goal state with infinity, then that route will never get selected, and we will always miss out the route that really get to the goal state. Okay? So we should always, we never overestimate our path cost when we are working with A-star search. So any questions? Any questions? Any questions? Any questions? Okay. So of course, we can always make a elaborated proof on the A-star search, why A-star search need to have an admissible heuristic. That is a heuristic never overestimate stuff. But the real mathematical proof is so involved that I believe that it is not necessary for us to discuss it in this course right here, because this is not a mathematics course. Okay, but I at least give you a layman explanation. Okay, just imagine you overestimated the path cost of the path, overestimated the path cost of the shortest route to the goal state with as infinity. Then you will never select that route, and you will never get to search out that shortest path. So that is the reason why you don't want to overestimate the path cost when you are working with A-star search. And we will always call the heuristic that never overestimate stuff as admissible heuristics. Okay, so this is a terminology you must remember. Okay, okay. So this is a terminology you must always remember, such that you can communicate with others using standard terminology. Okay, I don't make this terminology up. Okay, you should always remember those terminology, such that you can communicate with other scholars in the future using the same terminology. Okay, okay. And here is the source. Wait. Here is the source code on the alpha on the A-star search. Okay, and if you take a look on the A-star search, it is again substantially similar to the uniform call search. Okay, but the major difference is the argument. Here in the uniform call search, the heuristic, the priority value is the path cost of the node, And in the A star search, the priority value is the path cost of the node and the heuristic value of the node. Okay? So just doing these minor changes to the A star search, and we are able to convert the A star search, to convert the uniform call search into A star search. Okay? 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 So this is the major differences right here. Okay? Okay, so actually no major thing have been changed, okay? In the A star search and the uniform call search, we only make changes to this one, to the heuristics to the priority value, okay? And this is the major changes we have done. Okay? Okay. And A star search is something that everyone would be using, okay, in daily life without realizing it. Okay. The reason is that nowadays all modern computer games that needed to compute the path of the characters would use A star search. Simple as that. Okay, so if you have a game that the characters need to compute its path to get from one place to another, we will actually use the A star search. Okay, and its execution is essentially the same as the Romini Turing problem. Okay, in the computer games we are playing nowadays, it just turns the game map into a state graph like this, and then it use heuristics similar to the heuristics we show in the PowerPoint right now to do the path calculations, to calculate how the characters in the game need to move to get from one place to another. Okay, so that is why you will be learning the A star search algorithm in this course. Okay, you may find that all these techniques is something that is old school, but they are standardized algorithm that is used in daily life, especially when you're playing with games. Okay, A star search is a must, is almost a industrial standard for solving the problem of finding a route from one place to another in the game. Okay, and all your AI characters in the game depends on this algorithm to seek out the path for moving. Okay, so any questions? Any questions? Any questions? Any questions? Okay. So if there is no question, and now it is 1:30, okay? I believe that most of you are hungry right now. So let's stop today's lecture. Now let's stop today's lecture right here, okay? Next week we will actually go through the A star search dry run examples, and then we'll talk about search algorithm that is beyond classical search. Okay, and then now we'll stop